Good morning, everybody. Today we're going to start talking about vapor pressure. Vapor pressure is the first of the physical chemical properties of organic compounds that we're going to discuss. It's important because it does matter in the real world. For example, if you have a spill, like an oil spill, the rate at which the chemical evaporates and the extent to which it evaporates is going to be dependent on the chemical's vapor pressure. Another example of how it's important is when you apply pesticides, typically you apply them as some sort of liquid. Could be an aqueous liquid, or it could actually be a non-aqueous liquid that you spray on the fields. And then the rate at which the solvent evaporates determines how well the pesticide itself is going to be spread over the leaves. And it's also important because it's going to lead us to other important things like the Henry's Law constant, which is the partitioning of the chemical between the aqueous phase and the gas phase. So vapor pressure is important. And one of the other reasons that we start with vapor pressure in this class is that if we go back to this really simplified diagram that I have shown you at least once before, and you'll see it many, many times as we go through this class, one of the things that is useful about starting with vapor pressure is that vapor pressure represents the partitioning between, oops, that's not what I wanted. One of the things that's useful about starting with vapor pressure is that vapor pressure represents the partitioning between the pure phase here and the gas phase. And in the pure phase, you can assume that you have ideal behavior. And the reason you can assume that is because the chemical is in a pure phase with itself. It's, for example, if we use benzene as an example, it's one benzene molecule surrounded by a whole bunch of other benzene molecules. And they're all exactly the same. And so you can assume that their behavior relative to each other is ideal. And then if you go to the gas phase, hopefully you guys remember the ideal gas law. And basically what the ideal gas law is saying is that a gas is a gas is a gas. It doesn't depend on the structure of the chemical compound. It doesn't depend on anything else except the temperature and the pressure. And so in other words, you can assume ideal behavior in the gas phase. So you're assuming ideal behavior in the pure phase, and you're assuming ideal behavior in the gas phase. And so the vapor pressure, which is the symbol for it is this. The P for pressure, the 0 for equilibrium, and the L stands for liquid, because at this point we're talking about a liquid vapor pressure. Or it could also be an S here if we're talking about a solid vapor pressure. Anyway, the partitioning coefficient here, the P, is partitioning between an ideal phase and another ideal phase. And so the interactions are very simple, and so it's just a good place for us to start because it keeps life simple. We want to start with the most simple concepts and move to the more complex, and the way we do that is by starting with vapor pressure. In the original version of your textbook, this is edition 1. The edition you're using for this class is edition 2. There is a third edition out there, but I don't like it, and I decided not to use it. But in the first edition of your textbook, it gave these kinds of plots for all of the different physical chemical constants that we're going to talk about. Vapor pressure, Henry's Law, KOW, everything. And what it's showing you here is sort of the typical range of vapor pressures that you might expect for a variety of organic compounds, okay? So you have everything here from your aliphatic hydrocarbons. So those would be the kinds of things that are used in gasoline, for example. Octane is an aliphatic hydrocarbon. You got your polycyclic aromatic hydrocarbons, which are products of combustion. You got your PCBs, which are my favorite chemicals in the whole wide world. And they're what's putting my kids through college. You got your chlorinated benzenes, alkylated benzenes. These are important fuel components as well. And then you got your halogenated compounds that have 1 or 2 carbons on them. These are very important as solvents. Things like perchloroethylene, tetrachloroethylene, carbon tetrachloride. Those fall into this category. And so you're looking at the typical range of vapor pressures. And you can see for these halogenated C1 and C2 compounds, your range of vapor pressures is up here. It's in atmospheres. So it's about almost 1 atmosphere down to about 10 to the minus 2 atmospheres. Alkylated benzenes have lower vapor pressures. Chlorinated benzenes even lower. PCBs, very low vapor pressures. And of course, they range a lot. PCBs with only 1 chlorine might have a relatively high vapor pressure, around 10 to the minus 5th atmospheres, but when you get down to the PCBs that have 10 chlorines on them, this is the decachlorobiphenyl, also known as PCB 209. It's got a very low vapor pressure here, around 10 to the minus 12 atmospheres. And PAHs are kind of intermediate here. In the middle range, alkylated compounds a little bit higher. So this gives you a rough idea that you're looking at a range from about 1 atmosphere, which is a chemical that barely is even a liquid at room temperature. If you get above 1 atmosphere, the chemical is a gas at room temperature, right? All the way down to 10 to the minus 12 atmospheres. So you're ranging 12 orders of magnitude in vapor pressure. And so what's important about that is to recognize that, chemicals are very different. And chemicals with a high vapor pressure are going to behave very, very differently than chemicals with a low vapor pressure. Now, keep in mind, even though the vapor pressure may be, quote unquote low, it still can have an important amount of the chemical in the gas phase. So for example, the PCBs here, most PCBs, about 90% of all the PCBs you find in the atmosphere are in the gas phase, and only 10% of them are sticking to particles. So even though some chemicals have a very low vapor pressure, they can still have an important air transport mechanism and still be transported via the air. This is the phase diagram. You've probably seen this before in your general chemistry class. And it's just plotting the phase of the chemical as a function of temperature and pressure. And remember, since we're talking mostly about the gas phase here, temperature and pressure are the only things that matter. So this is your phase diagram, and what your phase diagram is telling you is that down here at low temperatures, you're in the solid phase. Once you get here to the melting point, right here, then you transition into the liquid phase. And this curve here is the temperature at which you transfer, the compound transforms from a liquid here to a gas down here, okay? So that is the boiling point of the chemical at different pressures, okay? In the world that you and I live in, the atmospheric pressure is right here at 1.013 bar, and so the temperature here that corresponds to that pressure is the boiling point of the chemical. So at one atmosphere of pressure, or 1.013 bar, this is the boiling point. And so that's a number that you could look up in a textbook, and it gives you an idea of what the vapor pressure of the chemical is going to be. So anywhere between the melting point and the boiling point, the chemical is mostly existing as a liquid, and then it has some measurable vapor pressure, right? Again, some measurable amount of it is in the gas phase, but it still exists as a liquid. And then when you get above the boiling point, strange things start to happen. So you no longer really have a liquid phase. Your chemical has just completely boiled away. But if you get to very high pressures, up here, you can still have the liquid phase. But, that's not really very relevant to us because we're not living on Saturn. We're living on the Earth, where our pressures really never get above the 0.013 bar. So it is possible to have a superheated liquid, and then when you get to really, really high temperatures and pressures, you can have supercritical fluids. Those are not very important for us. We don't really care about them, so I'm not going to talk too much about it. But the only time when environmental chemists might care about supercritical fluids is if you're using supercritical fluid extraction. And what that is when you're using carbon dioxide and you're putting it under tremendous pressure so that it turns into a liquid again, and then you're using that as the solvent to extract things out of your sample. And the reason that that's nice is because then when you're done, you just let all the CO2 evaporate off and you're left with nothing but your chemical that you're trying to extract out of your sample. But again, not something that we really have to worry about too much as environmental people. So hopefully from general chemistry, you remember the ideal gas law. Pressure times volume is equal to the number of moles of the gas times the gas constant times temperature. Temperature in this equation should be in degrees Kelvin. And the ideal gas constant, R, is something that you can very easily look up on Wikipedia. That's my main reference whenever I need to know R, because R can have a number of different units. You might remember from Gen Chem that it can have units of liters per atmosphere mole Kelvin. It can also have liters of joules per mole degree Kelvin. So it can have a lot of different units, and also it depends on whether you're using units of pascals for pressure or you're using units of atmospheres for pressure. So there's a lot of different values of R out there. And so that's why I always just go to the Wikipedia page and type in ideal gas constant. And then that will come up and it'll give you like every value of R you might ever need. We're going to break there for a new lecture, new audio. So the new audio will resume here on the slide called Temperature Dependence of Vapor Pressure.